Let's continue with the back page of 9193 review worksheet. Number 7, we have summation of n to the negative 2/3, which we can rewrite it as 1 over n to the 2/3. If you want to evaluate whether what the sequence converges to, find the limit as n approaches infinity for 1 over n to the 2/3. As n approaches infinity, the sequence will just converge to 0. Because it converges to 0, our nth term test for the series must also be inconclusive. However, this is in the form of a p-series, so the p-value here is 2/3. If 2/3 p-value is less than 1, then we know the series will diverge. Okay. Number 8, we have 3n over 2n squared plus 3. If we want to evaluate finding the sequence, if the sequence converges, we just evaluate the limit of the rule of sequence, and we see that the degree is higher in the denominator, so we know we'll go to 0. Nth term test for part B is inconclusive, so we can't do nth term test. However, this is in the form of being able to be using integral tests. So let's look at our condition. Each consequent term will be positive. Each term will be decreasing, and the function is continuous. There are no breaks in the graph. So we can just evaluate the limit as 1 approaches infinity, from 1 to infinity, for our rule of sequence. We go through u substitution. Our u value is 2x squared plus 3. Derivative is 4x. Going through u substitution, 3x stays initially. 2x squared plus 3 gets replaced with u. dx gets replaced with du over 4x. X is canceled out. We're left with 3/4 integral of 1 over u du. Replace u back in terms of the original variable, 2x squared plus 3. Evaluate the upper and lower bound. Plug in b representing infinity, and then the lower bound. And if we evaluate the limits as b approaches infinity, we're going to see that this expression will go to infinity. So if the definite integral diverge, then by integral test, our series must also diverge. Number 9. If we look at this form here, first off, part A, sequence will converge to 0, simply because this is in the form of a geometric series, and we know that as n approaches infinity, this will get smaller and smaller, affecting that 4, and will go to 0. Now, this is a geometric series that also converges, so just by the form that this is a geometric series, we know if the ratio is less than 1, which is 2/7, then we know series will converge. And because this is a geometric converging series, we also can find the infinite sum. Infinite sum is the first term divided by 1 minus r. The first term, we always just plug in the first n value into the expression. So n is 1, so 4 times 2/7 is just 8/7. So we get 8/7 over 1 minus 2/7. So if we're starting at 1, this should be 4 times 2/7, which is 8/7. So then 8/7 divided by 1 minus 2/7. 1 minus 2/7 is 5/7. So 8/7 over 5/7. The 7's cancel out. It should be 8/5. So the series converges to 8/5. Okay. We have number 10 here. Summation of 3 over pi to negative n plus 1. Now, if we expand this out, we get 3 over pi to negative n times 3 over pi to the first power. 3 over pi to the first power we can factor out or we can pull out as a coefficient. And then 3 over pi to negative n, I can flip that to be pi over 3. If I do pi over 3, I can see that this is in the form of a geometric series. Pi is greater than 3, so we know that the ratio is greater than 1. So because the ratio is greater than 1, the series will diverge by the geometric series test. Number 11, summation of 4 over n cubed. The limit as n approaches infinity. The rule of sequence will give us 0, so the sequence will converge to 0. But the series, this is in the form of a p-series, so our p-value is greater than 1 since n is 3, so we know the series converges. Okay, number 12, 5 to the n over n squared, 5 to the n over n squared. Going through comparative growth rates, we have factorial over polynomial. Factorial will grow at a faster rate than the polynomial as n approaches infinity. So we know the sequence will diverge. And if the sequence diverges, there's no chance that the series can converge. So the series will also diverge, but the reasoning here is by the nth term test. Number 13, we have 3 to the n plus 1 over 2 to the n. I can expand the 3 to the n plus 1 as 3 to the n times 3 to the first power. I can put this as 3 over 2 raised to the nth power, factor out the 3. Now notice that this is now in the form of a geometric series that diverges because we have a ratio that's greater than 1. So first off, we know the sequence diverges. And the series must also diverge by the geometric test. Geometric series test, since the ratio is greater than 1, so series diverge. Okay, so not quite the nth term test. This is the geometric series test. Number 14 here, we have 3n squared over n plus 2 times 2n plus 3. If I expand this out, I see that the degrees will match. And degrees will match, so limit as n approaches infinity will just be 3/2. So the sequence will converge to 3/2. However, because the limit of the rule of sequence does not equal to 0, we can say that the series diverges by the nth term test, since the limit of the rule of sequence does not equal to 0.